What's up?
How's your eye?
Oh, so much better. So, last semester when it happened to this eye, I can't see out of this eye already, so it didn't matter. So I was teaching wearing sunglasses for a while because it was gross. This one didn't get as bad, but like I said, Thursday it was just, I had to open it to see stuff, send email, call somebody, and then I could shut it and just talk to them. Hi. So, thankfully Friday, a little after I woke up, it kind of started opening on it. I was like, oh, thank God. I didn't have to go to have it open a little bit. Yeah, so dude, I'd never had them before ever. I don't know if anybody's ever had a sty or know somebody had a sty. I'd heard of a sty. I had read about sties. I had no idea what they were. And then I got one last semester. I'm like, no, this is not good. This should not exist. Got to shampoo my eye out with the tear-free shampoo. Yeah, that's exciting. Tear-free shampoo, but it's still like, right? And then you got to stand in the street with water. Anyway, sorry guys. I'll stop. I can tell you some more horror stories about what I had to do for this eye, the one I lost my vision in. Shots in my... Oh, wait, so... enough of that. Me and eyes, we have trouble. But I'm better, thank you. Some of you guys are like, man, you could have had a few more days off. So if there's no further questions from homework, let's get back into 7.2. So I want to talk about 7.2. We'll look at some videos. I'll have you guys do the worksheet. We'll talk about 7.3, and we'll head out. I've still got to do old school stuff because I still haven't gotten a replacement Apple Pencil. Mostly because my mind was on other stuff this weekend. So I've got to do old school stuff over here. And if you haven't seen test 3, we're going to move it to the 14th. So next Tuesday will be review day. Okay, and this is just somebody asked me a question. So I believe, let me review a couple things just to get you ready for this worksheet I'm going to do later. Because somebody remind me, how can you tell if a fraction is going to have a terminating decimal representation? What does that mean, by the way? What's terminating decimal representation? What does that mean?
It doesn't go forever.
Doesn't go forever. Stop somewhere, correct? Does anyone now listen. Beautiful, because if a decimal stops, what's 0.2, for example, as a fraction? 2/10. And then you can reduce it, but let's not do that. What's 0.37 as a fraction? 37 over 100. So I don't care how far the damn thing goes. If it stops, I can just count how many places and put that many zeros. Is everybody with me? So if a decimal stops, it is automatically a fraction. Because I just have to put on the bottom, I put all the digits, and on the bottom I put 1, and then all the zeros for all the places, yes? 0.2 is 2/10, 1 place, 1 0. 0.37 is 37 hundredths, 2 places, 2 zeros. Crazy, neat, nice. Why can't the math, all of it be like that? Too bad. So let's answer my question. If I have a fraction, how can I tell if it's going to have a terminating decimal representation? It's got to have a bottom that can become a multiple of 10. And the only way the bottom can become a multiple of 10 is if it only has factors of 10 in it. What is 75 made of? Oh, Jesus. All right. Can we shut the doors? Miriam, can you? Thank you. And then Suzette, can you shut that? Why does anyone have does anyone feel like rushing to see if everything's okay? No. So why does anybody have an alarm? So 2/75, let's see if that does anything. Okay. That'll be 2 over 3/4, yes? 3 times 25 cents. Will that be a terminating decimal? No, it's got this stupid factor of 3, right? It's almost good. It's got 2 over 5 times 5, but then it's got this stupid factor of 3. Damn it. So what about 3 over 75? So again, the bottom would be what? 3 times 5 times 5. What do the 3's do?
Cancel that.
So I get 1 over 5 times 5. Let me stop for a minute. I really want you guys with me. So the whole idea of this is if the fraction is in lowest terms, because maybe something like the stupid 3, maybe it cancels. Is the bottom composed of numbers that go into 10, only numbers that go into 10? Yes, it's made up of 5s. Each 5, if I give each 5 a 2, they both become a 10, yes? It's that simple. So what do I want to multiply top and bottom by? How many 5s do I have down there?
2.
How many? So each one needs a 2. So I got to multiply by 2 times 2. So I got to multiply by 4. Yeah. So if I multiply top and bottom by 2 times 2, the top is 4. What do I get down here? I get 10 times 10, 100. So what is that as a decimal? 0.4, tenths, hundredths. Kick ass. Okay, I like it. And again, so that's a neat little thing that, to be really, really honest, until I taught this class, I never thought about it that way. I was like, oh, I never thought about it that way. But yeah, that's how you can tell. Just break the bottom down. If it's only got 2's and 5's, it can be written as a decimal, a terminating decimal. Now here's the really nifty thing. Any other fraction, like the first one, it had a 3 in the bottom, right? Any fraction that has a number on the bottom, a factor of the bottom that's not 2 or 5, it automatically, sure, Jeff, why not? It automatically would have a repeating decimal representation. That's neat. So either it's got only 2's and 5's, and so therefore it terminates, or it has some other factor, and therefore it's repeating. It would be some kind of a repeating decimal. Yes? Okay, maybe. So, real quick. 5/7. Does it have only 2's or 5's on the bottom? No. So therefore, it should be repeating. Let's see if we can see it far. Do you guys see? All right, let me see if you guys are really interpret this correctly. Okay, so what kind of fraction is it since the bottom has a number that's not a 2 or a 5? It's a fraction, it's a decimal that would go forever, yes? So it's a non-terminating decimal. Kick ass. And I just claimed that if it's non-terminating, it's a fraction that has a number on the bottom that's not 2 or 5. This one definitely does. Not only does it not stop, but it doesn't stop in a very specific way. It's repeating somehow. Can you guys see where this guy starts to repeat? How far does that go? That decimal goes forever. The calculator can only show me so much. Now, to be honest, this calculator's like, you could do better because it's got more freaking room. But we'll go. It just stops somewhere. Do you guys see where this starts to repeat? 7. So it's 7, 1, 4, 2, 8, 5. 7, 1, 4. Why is there a 3? Because it would be 2, 8. If it has to go there, it's going to round. So we say everything again. The bottom has something that's not a 2 or a 5. I'm guaranteed then that the decimal will repeat. My calculator rounds to make it fit, and that's why it's a 3 and not a 2. So it'd be 714,285, 714,285, 4 freaking ever. How would I write that then? As my calculator has enough of me talking. Good God, does this guy ever shut up? So how would I write that?
Is that where you put the line?
Yeah. What would I put the line over?
Everything before the second 7.
Wow. Yeah. Oh my God, I'm going to zoom down. So that's the trouble. Certain fractions will repeat, but they might repeat after 27. Oh man. All right. They might repeat after 20. Wasn't that neat? They might repeat after 27 places. Are you guys kind of with me? So I might not know because my calculator only shows me so many. But this is just kind of generally nifty to know. Okay. So coming back to something a little more everyday-ish. I think we did something like this last time, but of course you guys can't see it. I really, really hate the overhead, but it's too bad for me. So we talked about this already, but can somebody remind me, not how to do this, but how to show somebody why we do it that way. So let's start with this. How would I do this if I had to do it by hand? Line up the decimal place, right? Okay, does anyone remember why? That is always the more important thing. By the way, since I'm just now thinking about it, somebody at some point on a homework wrote, if the answer's right, then they must have done the right thing, or something like that. Is that true? That's the worst situation, trust me, dear God. The student gets the answer right, but they did the thing wrong, they just got lucky, and I take points out. I'm like, what the hell? Get the answer. That's one of the worst situations for a teacher. Like, okay, let me explain. So, the most important thing for you guys, you must not only understand why things work the way they do, you must be able to explain why things work the way they do. How would I explain to a student why I need to line up the decimal place? There's several possible good answers. Or you can all just sit there and wait for me to say, yes.
Just because it's like finding up like 300 plus 20. It's like you don't put the 20 into 300.
So it's lining up like terms.
Yeah.
Yeah, the 0 in 0721, what is the 0, that 0.0, what does that represent?
Tens.
The number of tenths. And in the 9.125, which number is tenths? The 1. So of course you can only add like terms. What's a more, so you can tell somebody that, but what's a more in-your-face way to show that? What is 0.0721 as a fraction? It's terminating, so.
Over
1,
1, 2,
721 10,000ths, right? Plus, how do you write this as a fraction?
9 and 1.
Yeah, improper.
9
I want it to be improper.
and
1, 2, 3. By the way, it's pretty cool. This is 9 and 125 thousandths, right? 1,000 times 9 is 9,000 plus this is this. So you can write it like that. You can write it like this. Okay, I like it. I like it. Now it's really in your face, the issue. Why can't I add those together?
Because it's not like denominators.
Yeah, not like denominator. So, who needs what?
The right one is there.
Yeah, this guy needs another to times 10, right? Now watch this. I would put 91250 and I would put 721. I mean now these can just be added because they have like denominators, right? But look what that means about the original problem. Look how the 0 lined up. Let me see if I can say this. Yeah, not the 0s. The 7 lined up with the 2. See it? So if you do this, you're reinforcing decimals or fractions. You're reinforcing how to write a decimal as a fraction. And then you're just naturally seeing that these want to line up. And then you can hit them with, well, why does that make sense? Because like terms. And then you put the 0 there, and why does that make sense? Because of that. Okay, maybe. So and again, one big idea that keeps coming up for us is when you're about to introduce a new topic, you try to build it off of something they already know. Right? It's called giving them structure. It's called scaffolding. So you give them stuff to hang later stuff on is the idea. Does that make sense? I mean, to me, that's the two main ways I think of it. Either just directly saying it's got to be like terms. That's why the decimal lining up makes sense. But this, if you write it as a fraction, is sort of more in their face. Oh, it just sort of naturally lines up the way that lining the decimal would do. Okay. I love you guys. We're doing right? Okay. I just look out at you guys. Some of you guys are like, yes. Okay. So let's talk about multiplying decimals. So here, let me see. Can you guys just take a minute before I even explain why anything works? Just let me see if everybody remembers how to do this. I want to do 12.4 times 0.02. Go for it. No calculator, obviously. I want 12.4 times 0.02. First thing is, you see how I didn't line up the decimals? Because you don't have to. Does anyone remember how to do this? I mean, the first level of this, ignore all the decimal shit and just, what's 2 times this? 8.
248.
4, 2, yeah. Now it's all about, where do I put the decimal? What's up? Sorry. Okay. Who remembers how to figure out where to put the decimal? Yes.
How many numbers are after this one?
Yeah, so I have 1 here, 2, 3. So I just go 1, 2, 3. You don't have to put the 0 in front, but we normally do it so the decimal doesn't get lost. Does anyone remember why we do that weird shit? Why do we do that? What's a way you could explore why? Yes?
Would it be kind of similar to like long division where you know?
Yeah, we're not dividing, we're multiplying. Well, oh, I see. Very similar reason, but it still requires the explanation. But yeah, you're right, Olivia, you're right. It's the same kind of reason, sort of. All right. What did we do just a second ago to investigate how addition of decimals work? We turn them into fractions. Okay, go ahead. Turn each one of those into a fraction, put them next to each other, like you're multiplying 2 fractions, yes? Let's see what happens. Some of you guys look very skeptical. Like, why the hell would I do that? So a lot of what you're going to be doing is showing students why things work. You're not going to be showing them all the time what they will do, right? Why something works leads to the process you use. You're not going to do this. Holy shit. You might have them do it sometimes just to get the thing down, but then you're going to show them the shortcut. But almost everything we do with just basic numbers, they're almost all shortcuts. So what is 12.4 as a fraction?
4 over tens.
Times, and what's 0.02 as a fraction?
2 100s.
Now, real quick. When I multiply fractions, do I need an LCD?
No.
Hell no. I only need like terms when I'm adding, subtracting. Can I add x and x squared? No, they're not like terms. Can I multiply x and x squared? Yes. So multiplication is a lot more relaxed than addition and subtraction. What happens here? So without reducing, and I don't want to reduce because I want this to become a decimal again, and if I reduce, I lose the tens. And then I'm not in the decimal anymore, right? So don't reduce, just what do you get on the top? 248, what do you get on the bottom? Right? Now, the process, I collected 1 decimal place and 2 decimal places. Do you see how 1 decimal place and 2 decimal places becomes 3 decimal places? That explains this shortcut. This is a shortcut. This is why it works. This is crazy important. Because the stronger a foundation a student has basic ideas built on, the more sense more math makes later. It's going to be on your shoulders to build a strong math foundation so they can handle math later. And now this will become that. Bam. So now we can develop a shortcut. Why do I not have to line into decimals? Because I don't need like terms to multiply or divide. Okay. Is that cool? Is that right?
And dividing works equals multiplying.
We'll get there. Yeah, dividing, I like it. It's sort of this, but sort of not. Yeah. That made sense, Jeff. So here, you guys do this real quick. Do this with fractions. Oh shit. 43.18 times 2.5. You can use a calculator to help you with big ass numbers. If you have one. If you don't, then just do long multiplication. You can use the calculator for the top, that's fine. So you get 4318 over 100. And here you get times 25 over 10. So now you know it's going to be some thousands. 4318 times 25 is 50 times. Somebody save it for myself. What is it, sorry? Oh, I have it written right here. 107,950. Is that right?
Yep.
Okay. Now this is interesting. We end up getting this, but doesn't this reduce? Chop, chop. So how do I write this as a decimal?
107.
Yeah, good. So 1, 2, so 1, 2, so 107.95. So make division by multiples of 10 just counting places. That's all they are. Okay. Now if I did this sorry, you guys are if I did this the normal way, I would just do this. No regard at all for the decimal place. Because it doesn't matter. That comes at the end. And then I would just start blah, 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 and carrying and bullshit. Yes. So the last thing I would do is to move 1, 2, 3. Because I see 1, 2, 3. Okay. All right, that's a process we know and love. But you have to explain why it works. Now we come to the division. So, can you guys please do this division problem? Set that up, long division. I just want to see if you remember what to do. So it would be this here, right? What do you do? Yeah, in fact, very often you forget why you do this, but don't you just, if you move this over twice to make it a whole number, you gotta move this over twice?
Yep.
Does this sound familiar? A lot of times people say, okay, that's what I do. And I say, why? And they're like, that's what I do. What do you want from me? Right? But why does that work? Why does that work? How do I make the bottom become whole number?
Multiply the top and the bottom by the same.
What do I multiply by specifically?
100.
Yeah, because of this guy, right? Multiply by 100, that would make him become a whole number. Oh. Multiply by 100, it doesn't matter what the top becomes. All that matters is what I'm dividing by. I don't want to divide by a decimal, dear God. Thankfully, I never have to. So just moving each thing by the same number of decimals is equivalent to multiplying top and bottom by the same multiple of 10. And we're allowed to multiply top and bottom of any fraction in the universe by the same thing as long as it's not 0. All right. Here, so you guys, can you do this problem using fractions. Man, I really can't write worth anything. It's amazing. Why'd you drop? The guy can't write. Did everybody get their quiz back? Oh wait, I got other stuff here. What happened? Everybody else good? Anybody else not get their quiz back? All right. So here we go. All right, so how do I write this as a fraction?
Over 1,000.
1,000 divided by, how do I write that?
48 over
48 over 10. How do I divide fractions? Multiply by the reciprocal. What immediately happens?
But 120 on top and.
No, no, no,
Get caught.
no, no. What do I definitely want to do first?
Reduce.
Yes. So I can kill a 10, yes? What else happens? Sure.
12 and the 48.
Yeah, 12 goes into 48
4 times.
4 times.
So it's 1 over 400.
1 over 400. Now, is that a fraction that I can represent as a decimal?
Not really, because you have to figure out how 400 goes.
Well, part of it's already good, right? The 100? So the other part says not good is the 4. Is that cool? Can I make 4 become a multiple of 10? Hell yeah. Because multiply by 1.
5 or,
4 is 2 2's. So how many 5's do I need? I need 1 5 for each 2, so I need 2 5's. I'm going to multiply by 25. Yes? If 4 times 25 is 100. So I can make the bottom become a multiple of 10 if I multiply top and bottom by 25. Do it. Oh, wait. Change that into a decimal.
so 25 over 4,000.
Times 25 times 25. Watch how you handle the bottom. What's 25 times 4? 100. And I had 2 zeros. Bam. And then what is that as a decimal? 0 0
0.
2 5. Do you need one more 0?
Yeah,
1 2 3 4.
so it's 3 zeros.
1 2 3 4. So let's see. Tenths, hundredths, thousandths. Tenths, hundredths, thousandths. 10,000s. And isn't this 10,000? Okay. I'll put the list. Is that okay? You sure? Yes? Which one, sorry? Oh, up here? Just because we noticed that I could write this as a decimal. And how did we know? Because the bottom only has 2's and 5's, right? So then I could turn it back into a decimal. I lie. I got it all. Alright, so. How would you do this long division way?
It's
What'd you put outside? 4.18. I've got to move this over once. Nope, because it all depends on this guy. All I want to do is divide by a whole number. So this gets moved over once. So I'm now doing 48 into 0.12. And what happens here? Can 48 go into 12? No. So what do? Add a 0. Cool. Can 48 go into 120? Yes. How many times? 2, because 3 is too many, right? What's twice 48? So what would I actually put up here?
0, 0.
You guys remember this? And you see how we're going to end up with this answer, right? Twice 48 was twice 50.
Thanks.
Yeah, it's 96, so twice 50 is 100. You got to subtract 2 twice, so you get 96. 96 plus what is 100? 4, and then you got to go 20 more, so that's 24. Bring down a 0. How many zeros could I add? As many as I need. Don't worry, I'm not going to make you do a lot of long division where you have to go out to the 11th place. No, I'm not all about that. 10th place, yeah. No. I'll bet you anything that 48 times 5 is 240. Let's check it. 5 times 40 is 200, 5 times 8 is 40, 5 times 40 is 240. Kick ass. That is quicker than this, but not by like a lot, to be honest. Okay, I like it. Okay, I don't have to do that one. No. Oh, okay. Who remembers anything about this idea? Scientific notation. Yes.
Is that using E? Like,
Sure, on the calculator it's got a little E, but it represents something.
it represents like
How many
decimal. Once you have to get to make it.
How many times you move the decimal place? But that is represented by something. What would you do to 0.3 to make it become 3? Multiply by what? If I have 0.3, what do I multiply by to make it become 3? 10. I love it, right? What do I multiply 0.03 to make it become 3? 100. Isn't 110 squared? Alright, so the whole idea of scientific notation is, here's the idea of scientific notation. If I have 4,000, that would be 4 times what? 4 times how, what? 4 times 1,000, yes? But what is 1,000? How many tens is 1,000? How many tens multiply to make 1,000? No, not what do you multiply 10 by to get 1,000. How many tens do you multiply to get 1,000? 1, 2, 3 zeros. So multiply 3 tens, yes? Okay. What's the shortcut? Instead of doing this step, where's the decimal currently? At the end, it's understood to be here, right? How many times do I have to move it so that I have a single digit in front of it? Every time I move that decimal, that represents a times 10 I need to make it become what it used to be. What do I multiply 4 by to make it become 4,000? By 1, 2, 3 tens. That's what that means. When do I use scientific notation? If I'm talking about how far away stars are from each other, I do not want to say, that star is 87, 0, 0, 0, 0, 0, 0, 0, 0. Holy shit, dude. I want to say something like it's 8.7 times 10 to the 13th light years away, right? That'd be a much better, oh, that's a really far away star, but it won't. Is that coming back? Maybe come back. What about 0.004? How do you write that as a fraction?
4 over 1,000.
And did we just say that 1,000 is 10 cubed? Does that have the same form as this?
No.
Nope, not yet. I want to force those 3 10s up. Are those 3 10s happy right now? Yeah, look at them. They're all positive. They love shit. If I force them to go up, what happens? Negative power, which is telling me they want to be down. If you ever move something from one side to the other of a fraction bar, you got to have a negative power. Because that tells me it wants to flip back down. Does that sound familiar? You guys remember scientific notation? The negative power meant you move it a certain... Okay. Confession time. I still kind of stuck with left and right. If somebody's telling me how to get somewhere, they're in the passenger seat, and then I turn left, I'm like, oh, the one that makes it L. Good. So when I was taught this, what really sucks is, depending on if you're going from decimal to scientific notation or the other way, the negative means you go left or right. It depends on which. So what I always think is this. 4 times 10 to the positive 3 is going to get bigger. So if I have a big number, it's a positive exponent. If I have a positive exponent, it's a big number. I don't have to think left and right. I just make it big. If I multiply by 10 to the negative third, that's actually dividing by 10 over and over. So of course I'm going to get a small number. So I don't think left and right. I think negative power small, positive power big. So can you guys write this in scientific notation? Jeff. That's awesome, Jeff. You're doing great. The key thing, and this is going to sound really strange, but just to solidify your opinion to me as a very strange dude, I look at scientific notation as a tens vampire. It wants to suck all the tens out of something. That's why I want the decimal to end when it has a single digit in front of it. If I move the decimal to be behind the 9, doesn't 1,249 have a lot of tens in it still? Okay. So I want to move the decimal until it's after what number? The 1. I want a single digit in front of it. If I stop at 12, 12 is 10 and 2. It still has a 10 in it. Okay. So all this boils down to now is just how many times do I move the decimal? 3, 6, 9, 10, 11. So it'll be 1.249 times 10 to the 11. Okay. A little more concise, and if I rounded it to be like 1.2 times 10 to the 11, that's a much more concise way to reference that number. Instead of writing all those frickin' zeros. Now imagine the guy talking about distances between nuclei inside of an atom or something, inside of a molecule. It's like, holy shit, I don't want to write 0.0000 forever. No. Yes. Did I miscount? 3, 6, 9, 10, 11. Yeah. Okay. What about the other way around? What if I have 2.17 times 10 to the negative 7th? What would that be as a decimal? There's a bit of a shortcut. Move the decimal how many times? Which direction?
To the left sometimes.
Yeah, make it small. That's what I think to myself. How many times do I have to move around just to get around the stupid 2? Once. How many do I still have to move?
6.
So then it's going to be how many zeros?
6.
So when you have a negative power that kicks ass, you're going to have, if it's a negative 7, I'm going to have 6 zeros in front. That's a beautiful shortcut. Yes? It's just because I've got to move it once to get around the whole number. So I'm just going to go 0.123456217. So very often in astronomy, in atomic physics, whatever, we'll say stuff like, that's on the order of 10 to the negative 7. Because the most important thing about that number is not the 2, the 1, 7, it's the 10 to the negative 7. That's the most important thing about that number. It gives me an idea how small of a distance I'm talking about. If one star is on the order of 10 to the 8th light years away, then I don't need to know the other numbers. That's the most important thing about the number is how many freaking zeros would there be at the end of it. I love you guys. Okay. Oh. Okay, beautiful. So let me show you some videos. Then we'll do a handout so I can shut up for a little bit. You guys are like, that sounds fantastic. Oh, let me not record. So The author doesn't have to. Back to fractions, you're sort of making sense. You're sort of seeing where he loses touch with the math. Start with the fractions, make sure he understands fractions. If he does, then you can see where the disconnect is to the decimal. Any other, so obviously 0.2 times 0.3. Let's look at this. This is a really neat question, and I understand if you don't agree with me. 0.2 times 0.3. So if you do fractions, that will be very obvious, right? This is like we did earlier. That would be 2/10 times 3/10, which would be 6 So if you step back with him, you make sure that he actually understood the fractions that they did before. And then he can't argue with this, but it's still, all right, this becomes 0.06, which would show him that it can't be 0.6. And again, but how do you address his bigger problem of multiplication always makes things bigger? I mean, this shows an example where it doesn't, but it doesn't really explain to him why it doesn't.
What was that thing you did where you like shaded in part of like grid and then shaded in?
Yeah, so when you have like a rectangular array method for multiplying fractions, yeah. So then you get like a smaller part of the whole.
Yeah.
I like it. Okay, so you can have that visual, but still, that requires me to go back to fractions and use a fraction idea. Yeah.
0.2 times 5. It's like you have a bunch of 0.2s and you add them together.
Oh, cool. Okay. So if you go with 0.2, even just let's do the one he did. What was it? 0.4 times 6. Was that? I think that was the first problem.
Yeah.
So then we can do. Well, if we do 6 times 0.4. So what Nathaniel's saying is, remember, what's 6 times 0.4 mean? 0.46 times. So you would take 0.4 plus blah, 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 right? And again, that would sort of reinforce this idea. I'm adding 6.4s. How about this? How about 6 times 1 is 6? That's crazy. 6 times 2 is 12, yes? So 6 times 3 is 18, 6 times 2 is 12, 6 times 1 is 6. So 6 times something less than 1 has to be less than 6. Do you see that? So you can sort of do that and show him, and that puts it in his face. All the whole numbers we've been doing act the way that you're saying. These aren't whole numbers anymore, right? So if you kind of step it back, 6 times 3, 6 times 2, 6 times 1, 6 times less than 1 has to be less than 6. Because 6 times 1 is 6. Does that make sense? So again, that's a way that I would think to say something to somebody. All the visual ways is really good because they're more visual, right? All this is good shit. You can come up with your own way of explaining something, but you have to be ready for that kind of misunderstanding. And you have to catch that kind of misunderstanding. Something else I was thinking about. We've done something like this before. Isn't 0.2 2 times 1/10? Isn't 0.3 3 times 1/10? So I get 2 times 3 is 6, and then I get 1/100th. Which again is still going back to fractions, but okay. Alright, good. So there's no perfect answer as to how you would explain something, which is why I love asking that question for you guys, because I'll very often get a really good, well thought out response that I would have never thought of, which to me is exciting as hell. I love that shit. Yes.
Kind of expanding on like the less than 1 for the 6 times 4/10. You could also argue that like 0.2 like
Yeah, just to put this down there. Okay, that's what I was saying earlier.
okay.
Go ahead.
You could argue that like honestly, never mind. I was wrong.
Okay. I'm with you. Okay, that's fine. Okay. Anything else about that? The last video had some mistakes in it. It kind of kills me a little bit when he doesn't really help the kid out. You know, at the end, it's like, let's stop doing this shit. All right, kid, you're just not going to go in here. I was like, damn, help him out.
But what I've noticed in the videos is that he doesn't teach. Like, he doesn't, like, clarify things to them.
Sure.
He just wants to see where they're at, like
And-
what their understanding is without him like getting involved with what they understand.
And I'm not saying he's supposed to, because
No,
this
no,
to a
they-
certain degree is supposed to be looking at their thinking, purely their thinking. But it still kills me as a
Oh,
teacher.
yeah.
I'm like, but the purpose of the videos is to analyze a student's thought process. So to some degree, he's not necessarily supposed to coach them through, but I see nothing wrong with at the end saying, think about this, actually showing, going through a little bit, just to show people the different ways you can explain to a student, gets into understanding. But I agree with you. To a certain degree, he's not supposed to do that too much.
Something that I kind of remember when learning about decimals is always see everything after the decimal as if it's underwater. So therefore, if you're going 6 times more underwater, you're going in deeper. So like for example, like with that one, it's 6 times 0.4, like you said earlier, it's 0.4 plus 0.4. It's you keep going under the water with that point.
So if you have a 6 which is above water, and you multiply by something that's below water, you end up lower than 6.
Yeah.
I see. Okay, sort of. Like somebody, and you're trying to help them out, and you sort of sink in,
Yeah.
sort of.
So
Oh,
if you're going 0.4 underwater 6 times, you keep going lower and lower, making the decimal. So like,
sort of doesn't work there though, because you end up with 2.4, which still has a 2, which is like above water, right?
or was it with
But I
adding?
like the idea. Maybe it's like sinking the 6 down a little bit. That's what I was
I
saying. So
think
now it's only
it was-
2 above water.
It was something with adding. I don't think it was multiplying.
Oh, okay, okay.
Like to make sure that
Oh.
the decimal always lines up where the water is, like the decimal
Okay.
is where the water is, and everything else.
Oh, so
has
the
to line up.
decimal is kind of like the surface of the water.
Yeah.
And the whole numbers are out of the water,
Yeah,
and
yeah,
the
yeah.
decimal numbers, and again, that's how I say water. Sorry. Yes. Thank you. For a while, I was like making a joke and saying H2O, high quality H2O. So I like that. That's kind of cool. So the decimal is like the surface of the water. Right? So in this case, 6 would be above the water. The water? What's that? I can say it like, water. Can I have some more water? Alright, enough. Let me not offend an entire nation of people. Okay. But yeah, okay, I got that idea. So the decimal could be like the ground, because very often when we talk about subtracting, we often think about digging is minusing numbers, and then climbing is adding numbers. So having that surface be the dividing point is sort of like what you're talking about,
Yeah,
the
yeah.
decimal being the water
Big-
surface of the liquid. Okay. Okay. Oh, did I turn that back on? I think I did. There we go. Oh, let me give you this. Let me shut up for a little bit. So today, you'll be very excited that I have all new little symbols. We'll see how you guys feel about them. Let's see, 2, 4, 6, 8, 10, 12, 14, 16, 17. I'm bleeding people. Oh well, we gotta put a band-aid on the door. So let's see what happens. Let me think. Yeah, sure. We'll have about 2 per, except for one group. So 3 will do that. Some of you guys are tomatoes, some of you guys are sandwiches. No. Sorry. Oh, I think. They give you one, yes. What are you? Ooh, it could be either one. What do you want to be?
She wants to be a sandcat. She just said that.
I'll be a sandwich.
Yeah, just sounds cool. I like it. Starts with the same 2 letters. Because that won't let it happen. Ah. So find your people. So there are some of you have paints. Yes? Any paints? Who's got paint? Nobody's got paint. That's interesting. Okay. There should be more than one person with a little paint thing. No? This is interesting. Okay, let's try. Who's got violin? Little violin, little string instrument. There we go. Look at that. Okay. Okay. Who's got ice cream? Anybody got ice cream? Well, that's funky. That works. Too bad. Sorry. How about tomato? Anybody got tomato? Tomato, there we go. That's the tomato or tomato. I don't know how you say it. So good to go. Tomato. Could you wash my tomato in some water? Okay. Rockets. Where are my rocket ships? Rocket ships. Get together. Sandcastles. Where are my sandcastles? Oh, look at this. Your sandcastles. Get together, your sandcastles. Now, let me see. Did nobody end up with, wait. You have paint, and you're the only one. Oh, she's pink. I got you. She's going back someday.
I think I'm the only sandwich.
Oh, you're the only sandwich? Nobody's a sandwich? Oh, Miriam's a sandwich. Okay. So, Cam, why don't you pick a group and work with it, and then I'll do the same thing when she gets back. Yes? So pick a group, whatever you want to be. You're gonna move over to that. So this kind of goes back to chapter 6 a little bit. Little mood lighting. This one, okay. Understandably, this is, it's a little bit further back in the past, but kind of related to the way we did 3 times 5 with rectangular array method, kind of like the ice cube tray method. I could do something very similar here. It's a little bit weirder because the way we represent a fraction with a region model, which is what I meant to put here, is by shading. So the way you have to be really careful about this, and I'm going to be a little lenient with this, but I'll make this one 2/3, so then I'll shade 2 of these in. So that is 2 out of 3 of those bars. Pretend like they're all equally sized. So this is 2/3, and then this way I'm going to do 3/4. I'm going to slice it 1, 2, 3 times, and I'm going to shade the other direction. I'm going to shade 3 of those fourths in. So how many did I end up double crossing? Double hatching. Yeah, 1, 2, 3, 4, 5, 6. 6 out of 12, which of course reduces to 1/2. And again, another way, a visual way to show it's 1/2 is this is 6, and what's not shaded is 6. So exactly half of the picture is shaded. So that's why 6/12 is 1/2. And again, 6/12. Yeah, you can always check to make sure that your answer looks good. So when you shade very purposefully, so you can tell what the cross hatching is. There's the word, cross hatching. This guy. I actually had a group I gave a bonus question to that they had to do this without changing to improper fractions, and that becomes much harder. So of course the right answer is, very first thing is to make these both improper. What do you guys get with that? 11/3, I like it. Holy shit, what did I get? Okay. Times 24/11. And please, your God, I could multiply now and reduce later, but I would much rather reduce now, so all my numbers are smaller. And the great thing is, what do the 11s do? They kill each other. And what 3 goes into 24?
8 times.
Holy shit. Really weird. That, for a student to see this, can you imagine they're going to be freaking out? They're like, very ugly fraction times a very, very, very ugly fraction equals a nice whole number. Look at that. That's insane. That's infinity turned around. Oh, that's it. These guys, if you remember the process, is pretty simple. What do you do with this to see if it works as a terminating
You
decimal?
factor it out.
Yeah. The first thing I can see there is
25 and 100.
5 times 5, 5 times 2. So is that good?
Yes.
It's only got factors of 10 in it, 5 and 2. Good. Good. Now if you notice a number, a prime number that goes in that's not 5 or 2, you could be done immediately. What number goes into 280 that's not 5 or 2? 7. This is 7 times 40. I'm done. No. Or you can just start doing it and then hit it as you do it. It's either way. And this one, did you guys do this one?
Yeah.
This one ends up being nothing but 2s. This is 2 times 2 times 2. What is it? 7 2s? Blah, blah, blah.
2,
So
3, 4.
check. Is it 7 twos?
Yeah.
Okay. You guys all with that? Okay. Can anyone tell me anything about this fraction? If you changed it into a decimal, what would be true about it?
It wouldn't repeat.
It would not stop, but it would have a repeating pattern. Huh?
How would you tell everybody?
Oh, here's the beautiful thing. Either it's a terminating decimal, either the fraction given has a terminating decimal representation, or it has a repeating decimal representation. So how do I get a non-terminating, non-repeating decimal? Those come from stuff like screw 2, stuff like pi, right?
It's better than the English accent.
Sorry. That's fine. This is why I teach and I don't act. Alright, sorry. Now help me out. I have written this. And again, I keep saying this to you guys, but one of the hardest things, and I know you're going to be elementary teachers, but part of that means you're going to be a math teacher. So you're all going to be math teachers. One of the hardest things for a math teacher is to figure out what students did sometimes. And that's actually the most important step. Because a student could have done something really kind of nifty and made a mistake or applied it in the wrong time. You want to be able to celebrate that shit. You have no idea how many times a student has done something really kind of cool, but they just made a mistake somewhere. And if I wouldn't have taken the time, I would have just been like, this is wrong. Get away from me. So what did I do? Well, first off, is this right?
No.
It's wrong. Get out of here, Jeff. What is it that I did?
You squared the top of the bottom.
Good. I squared the top of the bottom. And you have no idea how many times I've seen this from all levels of mathematics. Because people just think, I can, as long as you do the same thing to top and bottom, like the same thing to both sides of an equation. No. What's the only things you can do to the top and bottom of a fraction and keep it the same? Multiply, divide by the same thing. Can't multiply or divide by 0, but anything else. So that's what he did wrong. That's why it's not correct. How would you explain it? You basically,
Draw pies. Like pie charts.
good. Go back to the drawings. Go back to the pictures. Go back to the physical representation. I like it. It would be a good first step. Which one of these is more than half? And which one is less than half? So I do appreciate, don't just make them into decimals because you're currently talking about fractions. You don't want to go to that level above fractions to discuss this. But can you guys all see 2/3 is more than half? And the student, you can get them to agree. Yeah, 2/3 is more than a half. And you can show them a picture if you need to. 4/9 is less than a half because 4/8 is a half and 4/9 is divided by more. It's going to be smaller. So there's no way in hell a number that's more than a half and a number that's less than a half can be equal. So that's kind of like a good computational way to show that this can't be right. It doesn't explain to him why what he did is wrong. But then you start talking about doing the same thing top and bottom, multiplying by the same thing. Here you multiply the top by 2, and you multiply the bottom by 3. You multiply by different things. Okay. Another way to do this is to apply his logic to something that's more obviously wrong. If I apply my logic to 1/2, square the top I get, square the bottom I get. If I do it again, square the top I get 1, square the bottom I get 16. And then you say to Jeff, you look at Jeff in the eye and says, are those the same thing? And little Jeff says, yeah. No, that's not so. That's another kind of use a more obvious problem and apply his same logic. So it's easier to see that it's not right. Okay. Okay. This guy, I've got to use a little bit of associativity, commutativity stuff, but what obviously wants to kind of go together? Compatible numbers. Well, sure, you could kind of do this straight across, but could you do half of 8? What's that? 4. 4 times 11? 44. You could do 88 and then half of 88, that's fine. I love it. So the whole idea is either like a fractional equivalent, at 0.5 is a half, or an even number times 0.5 becomes a whole number. What about this guy? Which idea are we using for this guy?
Decimal.
Sure, it's decimals, but what about fractions?
What's 1/4?
Yes, 0.25 is 1/4. And why is that really good in this situation? Because 4 goes into that easy, right? Well, 4 goes into 48.
1,203 times.
Yeah, 4 goes into 4 once, 4 goes into 8 twice, 4 goes into 1203. There you go. Another way to look at this real quick is if I steal a factor of 4 from him, doesn't this become 1? So I can do compensation. I can steal a factor of 4 from him. And in the process, if I steal a factor of 4 from him, don't I have to divide by 4? So mathematically, I'm looking at it in a different way, but I'm doing the same math. This one, not too bad, right? This one just jumps out at you. What am I using here?
Cancel. Negative, positive.
Compatible numbers. 1.94 goes with 106. $1.94 and 6 cents makes $2. $1.12 minus 12 cents makes $1. $1. How much water can I get for $1? And then finally, rounding. What number's in the hundredths place?
4.
4. What number do I look at?
5.
5. So what is this going to be?
59 and 95.
95 hundredths. Oh. Tenths.
9.
Yeah, so I look at the 0.9, and the number next to it is 4, so I'm going to keep it at 9. What it would have been a little more interesting, Jeff, is if I would have done this. How do I round that to,
Can't see it.
60.0.
how do I round that to the tens place? And you can see why this would trip students up. The nearest tenth, why can't it stay at 59.9? Because that wants to make it go up. But then it's really weird for them. So then you say it's either 59.9 or it's 60. That's the next nearest tenth. So it's got to be 60. Okay. And then tens, 60. Okay. So rounding always confuses students when you get to decimals, especially. All right. So one quick little thing, and then I'll let us out of here. Dear God, so we can all go home and curl up into a ball or whatever we got to do.
Did we finish chapter 4 just now, or just
Chapter 7,
or 7?
section 7.2.
7.2.
Yeah.
So we still have 7.3 and 7.4.
Yes. So I want to look at 7.3 a little bit. So guys, when I say the word ratio, what do you guys think? Fraction. I love it. Makes sense. Does a ratio have to be in the form of a fraction though? No. So really lame, no, it's not lame, but it's just, we use it all the damn time. The most obvious kind of everyday place where ratios come into play is when you're cooking, baking especially. So if anyone's ever baked and you have a recipe that makes 12 muffins and you actually have to feed 50 people. Then you have to figure out the proportions so you can get the right amount of eggs and so forth. And I know math, but man, I've made some stuff in the past where, oops, I put too much of this shit in. Holy crap, it's really cinnamony, I'm sorry. So a ratio could be, for example, miles per gallon. That's a type of ratio. So many miles to every so many gallons, right? So if I had a car that went 38 miles
That's nice.
every 1.2 gallons.
Dang.
I know.
I get that.
Does it exist?
Yeah, that is more than
I
that.
do it first.
Now my car goes about 21 miles every gallon.
Yeah, me too.
Mine goes
Yeah.
13.
Which kind of sucks, but oh well.
I'm ready to do that.
How would I write that not as a fraction, but as a ratio? Yes, 38 to 1.2. I could also write this as 38 to 1.2. So ratios are not fractions. They can be represented as fractions. I'm sorry? Oh. I didn't really put too much up there. What if I had 5 pets? No, let me not do that. What if I had a certain number of pets, dogs and cats? And there were 2 dogs for every 3 cats.
That's literally my house.
Say again?
That's my house.
Really?
2 dogs and 3 cats.
No way. All right. I'm sorry. Every now and again, my ESP, my mind reading kicks in at the weirdest times. I get nothing useful. So, how would I write that as a ratio? Now, what's funny is I didn't give you enough information. I want it to be a ratio of dogs to cats. What's that ratio? Dogs to cats. 2:3. 2 to 3. What about cats to dogs?
3:3.
I have too many colons down there. I have colon overload. What about dogs to pets in my house?
5.
2 to 5.
3 to 5.
2, thank you, 2 to 5. So this, remarkably enough, is called part to part. Not heart to heart, part to part. So this is another example of part to part. What do you think I call that? Part to whole. Good job. That would work too, but it's part to whole. Now the really weird thing about ratios is I could do pets to dogs. What would that look like? 5 to 2. This is like whole to part. So this is why, and what would this look like as a fraction? Yeah. Okay. Let me see. So that's some of the basics. If I have, so listen, all I said was there were 2 dogs for every 3 cats. What if I told you I had 20 total animals? 20 total dogs and cats in my house. Number 1, you're like, I'm not coming over there. I'm not coming to your house, man. I'm sorry. I wasn't late. So if I have 20 total dogs and cats, how many dogs do I have?
8.
How do you know?
I don't know. You have 8 dogs and 12
This is a
cats.
perfect example of this. Type of student, you're like, you got the answer, and you have no idea why. Listen. 2 dogs for every 3 cats. So if I had 6 cats, I would have, and that adds to be 10. So the multiplier, the total for 2 to 3 is 5. I want that to be 20. So what's my multiplier? If I had 2 dogs and 3 cats, how many animals is that? 5. I want 20. What's the multiplier? Multiply by 4. So if I multiply 2 times 4, 8. How many cats do I have? 12. 8 dogs, 12 cats, 20. So if I know the ratio, I do not have a clue how many total. Couldn't there be 20 dogs and 30 cats? Then you're definitely not going. You're calling somebody. This guy.
Can you rescue children?
Yeah, someone's gonna. You gotta help these animals. I won't say anything about a presidential candidate. That's all I'm thinking right now when I made that example. Weird. All right. What was the last thing I want to talk about? Where'd it go? Yeah. Oh, I already did that. All right, that's plenty. That's enough, guys. Let's all get out of here and enjoy the possible last few moments of democracy. I don't know. I'm sorry. It's hard for me to keep my politics hidden.
Well, let's hope Thursday you're in a chipper.
Yeah. Let's hope.